It's always difficult to decide what to talk about, right? But I figured if I'm, for once, we're talking about proper mathematics, I'm not going to talk biology here. I'm going to talk about some of the little proper algorithmic work we've done the last 5, 6 years at least. And I probably won't have time to actually get to the background here, but we'll see about that. What I'm going to start to talk about is really something that several speakers have touched upon here, really, that we're facing more and more heterogeneity, but we're also getting better and better at understanding and classifying that. And overall, I think that that message is very positive. We have a wealth of beautiful methods to handle it. But then I'm going to continue a little bit about the things that interest me most here, that how do we continue then from these micrographs and then go to maps that are possibly very heterogeneous then, but then actually derive proper molecular models of this? Because that's at least, I have a background in molecular simulation and stuff. I don't really care that much about 3D densities. It should be atoms. Uh, and that took us on a very long detour, but I think that we're finally on our way to cracking the problem, how to properly derive restraints to fit things into maps. There have been plenty of attempts at that in the community, and I think most of them have been wrong. And that enables us to even use restraints in maps to drive simulations. So we can actually start having an ensemble and visiting things and doing things like density-driven ligand fitting. So when we started, I'm a relatively newcomer in this field. So we got into all this when we bought equipment for a new cryo facility in Stockholm. And the idea at the time was, this is great. We're going to recruit a younger PI that can start doing structures of all my ion channels for me. And that didn't really work out. But eventually, I think that people in my team started working with Alexei Amund's group and everything. But it's great fun. I'm a disaster in the lab, but my students are not. But based on all this new software that we partly developed in Reliant, but there have been plenty of other teams that it's completely remarkable with the space, the speed with which you can do structural biology today. So this is Bijoya. This was her first biochemistry experiment ever as an intern. She determined a new chlororibosome structure in 24 hours. She's going to be so disappointed the rest of her scientific career that it's not that easy. But of course, it's amazing, right? You can get this structure, but well, this is not really a structure. So this is a whole part, it's a lie here. This is a density, that's not the structure. And that's kind of the problem. We're getting really good at determining these densities. As you actually, what you can see up here on the, I need this vitrified laser beam. As you can see, just to make things harder here, not only do we include the chlororibosome, just to make things harder, we deliberately include a bunch of junk fractions too, just to see if the computer can sort that out for us. And the cool thing is that it does. So you don't even need to do proper biochemistry anymore. That really bad students just throws a computer time at it, and the computer will sort out the stuff that you don't want to have there. But as we're getting more and more of these models, you can certainly apply things like the manifold concepts and everything and try to bring all of these things together. We do apply quite a lot of these things in Reliant, even for smaller things such as ion channels and everything. And one of the things that fascinates me most is that this has also enabled us to do, no, that doesn't work. That's a good place for it. To do focus classification. So once we find that there is a certain area of a protein or something that we know better, we might be able to learn more information about that. And the way we do that in Reliant in particular is that we try to automate the things that all of us have done manually for a long time when you somehow try to mask your system and everything. So what we can do in Reliant 3 now when we have multi-border refinement is, again, pretty much an automation of what we would do historically. The traditional way would be to just refine and iterate over one structure, and there have been several speakers that have brought up how we do this. But the point is that basically we need to optimize the orientations and alignments of molecules. And as we do this, we gradually up with better and better reconstructions. But if we take a complicated molecule or any shape, we can create masks for this and then say I have an orange and a green and a purple part of it. And exactly the same thing works here. We just introduce more variables because now we can rotate and rotate, tilt, possibly even translate these parts of the molecule relative to each other. And we're not really adding that many more degrees of freedom. And in particular, as we're getting more and more data all the time, this works quite well to optimize. And as long as we don't screw things up completely, these masks that we somehow have to create, as long as they cover the entire molecule together, and as long as they cover roughly the right part of it, the computers will just work it out. The details don't really matter that much. And what we then do is that for each of these parts, be it 3, 4, or 5, we optimize things. Well, first we create a consensus map of everything, which is just the standard way we do it. And then for each of these, we then try to focus on part 1, optimize the alignments and orientation for that, and then we do that for part 2, and then we do that for part 3, and eventually we bring all of these together into one large reconstruction, and hopefully have something that we're happier with. Now, the challenge with that is, by definition, that's not going to be one reconstruction, right? So these things are mobile relative to each other. And I have a couple of examples that yes, I think I'll have time to show you that. First, a very simple ribosome example, large small subunit, and a head. And we definitely get better individual representations of the bodies. But the point is that it doesn't stop there. So that the mere information about how they moved relative to each other tells us something about stuff we had in this data. So it's certainly nice to get a high resolution multi-body reconstruction, but in addition to that, I can now start to calculate what are the eigenvectors here. So in this particular reconstruction, the 100,000 images or something I had as part of this, how are they moving relative to the average multi-body reconstruction? And this even enables me to do, in some cases, I have a beautiful, clean eigenvector distribution here. So this definitely appears to be one more or less Gaussian motion. In this particular case, I have an eigenvector that's not entirely pure. So here I probably have 2 components of the motion and everything. But no matter what these look like, it's relatively easy to translate these to actually show what the motion is. So in this case, the red versus blue are the 2 extreme parts of the motion of the head and the small subunit relative to the large subunit. The ribosome here might not be a beautiful example, so I think we have the spliceosome. Here it's much more beautiful. So with the spliceosome, we even resolve an entire new domain here that we could hardly see without doing multi-body refinement. And you can probably see that there's a fairly remarkable difference in resolution. This is exactly the same micrographs. The cool thing that the data was there all the time, but by doing all the, but it's both 2D and 3D classification, we're basically averaging out the data. And this is the danger that I think we all want more images, we all want more data, but there is a memento mori here. The more data we collect, the larger the risk that we do things like that. Well, that really was part of your data. The other cool thing is that here we get really beautiful motions. They're large motions. You can even see that this small extra domain here, right? That it's moving a lot, which is likely the reason why we couldn't resolve it in the first place. And this certainly leads to higher resolution of each of these components separately. Although we have fewer particles per class in each of these cases, but we get better resolution. So we certainly want more data, but it's not a guarantee that you will always get better resolution the more particles you have per class. You need to be careful so you don't average things. What this also enables us to do, or at least roughly the same code, is that, apart from the 3D classification, I can also decide that there is a certain, let's say that I would like to improve this part of the molecule. And then I can create new masks here and redo all the classification just with a mask of that part that was moving too much or that I could not resolve yet. And I think I have a better example of that. So this is one of the chlororibosomes, again, that we work on with Alexei Amund's group. So here we found a interesting structural part here up on the right that we couldn't really resolve. It was a bit fuzzy and low resolution. So then we created a mask covering roughly that part. And again, that we probably included a little bit too much, which is fine. And then we got a bunch of classes where that part was better resolved. And then we used something like 600,000 particles and got a 3 angstrom resolution. So then we extended the structure just in that part slightly more. But the cool thing, we can do exactly the same thing again, because there was still this tip. We couldn't resolve the tip. So then we do another classification and now point just at the tip. And then we can do exactly the same thing once again. And now we get sub 3 angstroms also for the tip there. And of course, this ribosome is a bit of cheating because we have so many particles from them and everything. But in general, I feel that this is an approach that has legs. There is more data than you think in your data, and you don't necessarily need that many images. And that, I think, brings me to the next part. Yes, because the sad part, as I mentioned, I lied. It doesn't take 24 hours to determine a structure. It takes 1 month. Because when we had that map, you needed very skilled people in the lab, in particular Shintaro here, had to sit down in front of the computer and try to build all these chains into that map. And there are programs that can help you automate that a bit, but that is a far more labor-intensive job. And it's also something you definitely can't give to a first week's summer intern student. And at least for us, this is frequently becoming the largest bottleneck. How do you move actual structures, create actual structures into your maps rather than just getting the maps determined automatically? So for a long time, I've been, well, hey, I'm a physicist. I've been interested in the problem that can we actually optimize this part of the problem? And the other reason I'm interested in that is that we have a background working with molecular simulations. I really would love to be able to somehow derive proper restraints from the maps and add those as very weak restraints to bias my molecular simulations. So today you would sit down and do this in Qt manually, which kind of works if you're lucky. There are programs that try to do some sort of flexible fitting. MDFF is one of them, and these programs occasionally work. And the occasional part, it depends on the type of motions in your system. So you frequently end up with large distortions, that you're getting secondary structure elements that are completely destroyed and everything. And then you can try to rectify that by having a scaffold, so you apply lots of distance restraints inside of all your secondary structure elements. Now, that is fine if none of your secondary structure element actually changed. But if you have some of these secondary structure elements that should bend, right, you started by assuming that there are scaffolds and they can't bend, and then I'm not going to be able to bend them. So we wanted to solve this problem, well, in a slightly more appropriate fashion, and also one where we wouldn't need all these restraints. So Christian and my team spent like almost 2 years so on the one hand, we have the sample, and we do know with all the normal caveats that molecular mechanics might not be good enough, you might need quantum mechanics or something, but it should be possible to describe the conformational space of these molecules with physics. Same thing there, that there is an entire process. We can vitrify it, we can do a microscope experiment, we can calculate 3D densities and everything, and then we should be able to get back and somehow integrate or compare that with the molecular mechanics. And now I'm going to try, since this is matter, I'm actually for the first time in a very long time, I'm going to have some equations on the slide. If you're not an equation person, tune out for the next 180 seconds and I'll tell you when to wake again. In principle, the probability of seeing some sort of general conformation X here, and that can be anything, the probability of binding or the probability of seeing a molecule, given the vitrification, that is just proportional to the product of bias probabilities, so that if we vitrify the sample, the likelihood of seeing a certain configuration vitrified, and then we have to multiply that with how the vitrified configurations relate to the actual configurations. And what we all pray is that vitrification does not influence the sample at all. Sadly, I don't think that's true anymore. And with a tiny amount of mathematics, that actually means that the probability of getting a configuration as a bias based both on the images we had, the vitrification process, and the microscope is, again, a sum of products of probabilities. That is kind of important because it's not entirely obvious, and it's easy to... Images are not independent, in particular. If images were independent, you would end up with something like that instead, and that's usually not the case. Actually, so both Pilar Kosia and Gerhard Humendales have looked into quite a bit on how to determine that part. If you can determine that part, you've solved the entire problem. And if you're a young student getting into cryo and particularly mathematics, that might very well be where you should start looking, because computers will get more powerful all the time. Today, that would be too expensive to do because it would be hundreds of thousands, well, millions of images and hundreds of thousands of orientations and everything. So what we do is that we cheat, and we cheat by introducing these latent variables in form of the 3D densities. And this is literally cheating. The 3D densities, it is a nice tool and they help us in many ways, but in principle, we would like to get away from the 3D densities. We haven't been able to do it this far. And what both Reliant and a whole lot of other programs do, if you apply some sort of Bayesian approach to this, you can reformulate this slightly. So in particular, I can say, what is the probability of seeing a density given a configuration? And this is the second slide with equations. Now, if this model, that could represent anything, but you could let that be, say, the conformations of a protein or something. And that just means that if we now have a distribution of conformations, I should integrate over all that. And then again, it's a product of a couple of probabilities that describe, given a configuration of the molecule, how likely would it be to observe a certain density, etc. And again, skipping just a tiny bit of math, if we then assume that the scattering in each part of a large molecule on a grid or something is independent from scattering in the adjacent voxels, you can actually calculate the core part of this as what is the probability of seeing scattering in a certain part that depends on the local density. And then it ends up that we only have to evaluate that in each small voxel in the system. And if we make a reasonably simple approximation. That should depend on the number of atoms we have in this volume of space. It should depend on the chemical cross-section. That is how likely they are to scatter electrons. And if you do the math here, you end up with a binomial distribution. And for the typical numbers we have here, where the probability of scattering is quite low and we have lots of molecules, we can use the Stirling formula and everything to simplify this a bit. And this is the last equation. This means that we can actually get a reasonably good approximation for this probability of scattering. That's pretty much a sum of this is something that's basically a Kullback-Leibler divergence. And that's a well-known statistical formula and everything. We know how these behave and we can calculate them. And now you can wake up again if you didn't care about the equations. So the point is that what I had on the previous slide, there was one thing, there was one thing that we had these R's, right? That on the top here, you had the probability of R. And that basically means that if I don't know anything about the experiments, I need some sort of way of describing what is the likelihood of having a molecule in different conformations. And that we have tools that we can use to process, in particular a force field or something, or a quantum mechanical force field. But in addition to that, we also have this from the last line on the previous slide, we now have a fitting potential based on this Kullback-Leibler divergence, that if we apply this, I'm going to try to fit things into the cryo-EM density. And pretty much the only thing left to decide is at how much of the fitting potential do I want to apply in addition to the molecular mechanics potential. There are a couple of other things we might want to do, have some spreading and noise and everything, but in the interest of time, I'll skip that. But the beautiful thing, this is up with a very neat and simple function. This NV describes the entire statistical process that I had on the last slide, how likely we are to scatter. And the G there is a Gaussian spread, and then the F is the cross-section of each atom. But all of these are either well-known or we can just tune them slightly. And what that means is that I now can calculate a posterior probability of having different conformations of a molecule that is a combination of the prior, the force field or the simulation, and this fitting potential that I get from the cryo-EM density. And here's where things start to look pretty nice. So there are, as I mentioned, there are a few different ways to do this in literature. The traditional super easy way that MDF have pioneered is that if we have electron density, let's just invert the electron density and use that as potential and drag the electrons there. And that would be that part. Now, that works great in the sense that you put the electrons there, but if I have a particle out here, the problem is this particle is not going to feel any derivative here, right? So you get beautiful convergence if you're very close to it, but otherwise you're not going to feel anything. And the cross correlation, they're fitted up with roughly the same problem. But you see the solid black line there, the Kullback-Leibler. We have, in the ideal simple case, this is going to be anharmonic. In the non-ideal case, it's not going to be quite that easy. But the point is, I have a roughly constant force. So I have a beautiful convergence radius here. And if you look here on the right, that if I just create a very simple system where I have one large peak and a small peak on both the x and y axis here, but both the cross correlation and the inverted density end up with very rugged landscapes, there is no way I'm going to get any convergence to that and that point here, right? I would even argue that the inverted density here is completely wrong to only have density here. But with the Kullback-Leibler divergence, pretty much it doesn't really even matter how sharp or rugged the landscape is here as a function of sigma. I get a beautiful minimum there and a beautiful minimum there. So this is something that we started to like quite a bit. And we've actually implemented this in GROMACS. So this is just an example of a synthetic density. And in the interest of time, I have some units. One of the nice things with this is that it's actually not just a plain minimizer. So on the one hand, we account for the entropy and everything for the force field, but even if we forget the force field part and everything, the way we formulate this, we actually have an attractor. Sorry, this is not the same protein, but I realized. But the attractor here is not simply the density that the molecule would move into. And that's important because it means that I can actually go over the barriers. I'm not just going to fall into the closest local minimum and stop. Again, it's not perfect necessarily, but it's far better than either inverted density or cross correlation. So for this simple test case, where you actually know the answer, we can go from a bit over 7 angstrom RMSD down to 2.4. And this, I think, took 70 nanoseconds or so. In hindsight, we could have done this 10 times faster. Now, fitting it into the density, that's not a problem. But the cool thing, while doing this, we conserve all secondary structure and everything. I don't need to have any scaffolds or anything. So this is just like a plain normal molecular simulation of the protein. And when I'm actually down here, then I'm just keeping, I don't necessarily need to stop here, because here I'm actually sample the ensemble of a molecule under the side condition that I'm sticking to the part of phase space that corresponds to the density that I'm seeing in cryo. And that's important, because I think, hey, I'm a molecular mechanics person, but molecular mechanics is great locally. You will get hydrogen bonds right, you will get the local torsions right. Where simulations have a huge problem is getting large motions right, because we can't sample that. But that is the one thing we get from cryo. So the cryo basically forbids us, don't waste time in parts of phase space where we know you should not be. But while you're roughly in the right part of phase space, then we can start to investigate and sample locally, even then beyond the scales. Imagine that you had a 4 angstrom cryo structure. The force field will still help you to get some of the atomic interactions right that are probably beyond the resolution that the cryo density had. So this is yet another system that a colleague of mine, at the time I should have told it, I've added that it's a botulinum toxin now. So this is Paul Stenmark, who's now at Lund. This is a structure of a botulinum toxin where they had a previous structure in white, but they had a fairly large conformational shift here with the new structure. And same thing here, this took roughly 10 nanoseconds of fitting, which I think maybe 2 hours on a computer, on a single computer. And you needed the entire domain here to rotate and everything and move into it. We didn't have to apply a single restraint. I don't have to keep the secondary structure intact or anything. There are even some of the secondary structures that change a bit, which is perfectly fine. And is it perfect? No, it's definitely not perfect. But the neat thing is that this is something that happens over lunch. It does not take it wouldn't take 1 month to build this, but we are frequently limited, even for smaller proteins, but only the very skilled people in the group can do these things. So I would love for this to be better. I don't think it is better than the best humans yet, but the neat thing that this takes 2 hours, and it's a computer that does it automatically. So there are a bit of things that we might need to tweak, so that if you have some sort of black line here, that would be the underlying molecular mechanics function, and then we have a very weak fitting potential. The problem that happens is that when you add these to each other, we might still get stuck because the molecular mechanics might create energy barriers. That means that we won't go on. So that sometimes we need to bump up the force constant a bit, so we apply more of the fitting potential here, or even more. Let's see. Yes, we had even more. So what we do here, we even tune this so that if things stop going downhill, then we start to bump up the force factors here. So that if we stop the refinement, then we apply more and more refinement, and that's as the derivative then increases, then we take down the strength again. So this works remarkably well, actually. That once we start getting close to the end game here, then occasionally we go up in force, but since we don't really improve anymore, then we take it down again. So that this is still a little bit based on trial and error, but what I like with this is that we're not necessarily tethering the molecule very hard. So once the molecule fulfills the cryo-EM density, we're not really pushing it. Then we're letting it explore that part of phase space, which means that we're not just pulling it as hard as possible to the center of the density, but as long as you fulfill the density, it's free to explore the ensemble and sample things as if it was a normal molecular simulation. And I'm going to show you, I'm not going to talk about the biology here, but this is actually one for ion channels. Sorry, let's just pretend that this is a synthetic density. So we still, again, since we're still in the trial and error stage here, we typically start by smoothing this out so that we do a low pass, and then start by initially only considering the C alphas and everything. The point is that when we start this out, in this case, we started from a model at pH 5, and then we had 2 new structures at pH 3 and pH 7 that we know were undergoing slight conformational transitions. So, and in this case, the FSC we then have here turned out to be pretty lousy when we started. But then we start going over to the next level here. So when we move from 1 to 2 here, we improve the FSC quite a bit, in particular for the very low frequency stuff. Then we start to go to the intermediate parts here when we do a slightly longer simulation. Well, the longer simulation improves things quite a bit, in particular in the intermediate stages. Then we do a slightly longer second part of the simulation here. It didn't really help. And then eventually we move all the way to the sharpen map and run a very small things, and that improves things even more. And as we also see here, in general, it appears that we start by getting the low frequency things right, and as we're doing to sharper and sharper maps, we gradually move to start improving the higher frequency parts of the FSC. We can even do spectral fitting here, because if we do things on very high frequency, I can bin my voxels in the system, so that I can choose to basically apply different force constants as a function of the frequency. If you want to, you might, for instance, say that I want to apply a very strong fitting potential to the lowest frequency stuff, but this is a very low resolution map, so I don't want to apply any fitting at all to the highest frequency parts. And these are basically the end examples of the structures. I'm not sure how interesting that is to you, but it basically means that we can actually resolve, even though we've done completely automated models, we get, I think structures that are, to first approximation, just as good as the ones that Urska, my student, spent 2 weeks doing manually. And we resolve differences, the radii inside the pores and everything. But again, this takes less than 1 hour to run because it's an even smaller system. So you get these over lunch for free. Now, what can happen with the simulations, of course, that it's easy to screw up your structure. But in this case, it turned out that the initial model, when we ran through this through ProCheck, to tell the truth, it was not that good. I think it had 72% or so core torsions. But after this refinement, it actually got up quite significantly. So some 86%, well, 85% on the one. So we definitely get a better fit with the map, but we don't get a better fit at the map at the cost of distorting the structure. If anything, this structure is significantly better than the one we started from. And the reason for that is, of course, that the molecular mechanics force field will do that part. It will move the torsions to the right place and everything. Which brings me to the last part. We, just for fun, we decided to see, can we use this to derive, for instance, ligand fitting? So this is Joe in the lab, Jordan, that we took one of the recent glycine receptor structures. You can probably see a theme to the type of channels we're interested in. And this is a structure that had 5 strychnine molecules bound, which is an anticonvulsant. And sometimes I'm very hesitant about the value of, in particular, molecular simulation. Can we trust molecular simulation? And sometimes I guess it's a curse that you're most doubtful about the work that you've invested most of your time in. So if you look there on the top right, what you first do that if you remove the molecules, just put them out in the water. It's a membrane protein, but we put them extracellularly. And then you simulate this for half a microsecond or something in 5 copies. Nothing happens. They don't spontaneously rebind. And one obvious conclusion of that is, of course, the molecular mechanics force fields are completely crap. They're not good enough at reproducing this. On the other hand, we can do the opposite experiment on the lower right. We can start the simulations with the 5 molecules bound. And if you start them with the 5 molecules bound, they don't unbind. So that once you have the molecule in the right place, the simulation will keep them there. The problem is just we're not sampling enough. And that's exactly the problem that we solved with this density-driven restraints, right? So if we now start this, but remove the strychnine, but keep the density there. It's a fairly low density. It's not like, well, I'm not sure about you, but I can't say what the orientation of that molecule should be, so that's probably based on guesswork. At some point, we're going to need to have these molecules in reasonable proximity, otherwise it's going to take an eternity. So what Joe did is we can place these molecules randomly all over the system. If we place them very far away from the protein, we don't care. If you would like to be slightly smarter, maybe we should place them with docking or something. But then we cluster things with, well, either k-means clustering or any grouping so that we have maybe 10 different candidate binding poses or 100 or so. This is a very fast calculation, so that doesn't really matter how many we pick. And then we do this fitting that I just showed. So what frequently happens is that it takes a while for things to get quite right, and initially we might even have the protein drift in a bit that we need to fit the protein into the density, and that's what happens roughly halfway through here. When we get the protein right, then we start to get a significant force that actually drives the ligands into the right place too. And when the ligand starts going to the right place, the increase and the correlation you see here is that as the ligands are moving into the right place, this goes better and better. And this works pretty, let's see. This works pretty darn well. That appears to completely reproduce the pose. I was kind of shocked to see that. That might be a coincidence. But we get plenty of poses that are almost exactly the same, and a few ones that occupy the same volume at least, but I'm not sure about the orientation there. On the other hand, given the initial density, I don't think the experiment was either. And while we do that, the protein, we don't distort the protein at all. And this is without any restraints whatsoever on the protein. I don't try to fake the protein here. I don't keep that to the C alpha coordinates or anything. Now, that was still synthetic densities. I can do exactly the same thing against experimental maps. So now rather than having a synthetic map from the PDB file, I now apply the experimental map. This works really well too. Some way, I think it might work a little bit too well. So the green FSC curve here, that would be the FSC between the PDB file and the density generated from the experimental PDB file and the experimental density in the map. Now, if we start with a simulation to make things harder so that we don't start from exactly the same structure, we first run a 1 microsecond relaxation of the protein, during which it will drift away because it doesn't have the molecules bound. And then the FSC goes down, which is not entirely surprising. But when I actually do refine this, it goes up again. We have some sort of overfitting here, obviously. I'm not saying that we're way better than the experimental structure. It's not, in this case, it's not so much overfitting. We don't do gold standard here or anything because it's not that type of overfitting. But basically, at some point, if I try too hard to push my protein into the density, I do so at the cost of local distortions in the structure and everything. And we probably shouldn't be pushing quite that hard. But even here, the point is you get beautiful overlaps of the ligand placement. And even though we probably push too hard in this case, the protein is pretty darn good. There is not any obvious distortions or anything in the protein. And again, this typically takes between 30 to 60 minutes or so. It's completely automated, hands-off. And I think I'm pretty much out of time there, but I will sum up this in 2 pages. But I think where we would like to take this long term is instead of having the traditional approach that we have on the left here, where we collect our cryo-EM data and then somehow classify things into first 2D and then 3D classes and then do orientational assignment and then reconstruct from each of these. What we would like to do is something that is kind of similar to the manifold idea, right, and everything, but let these molecules be on some sort of reasonably high dimensional space and then gradually calculate the density. What is the likelihood of my simulation visiting different parts in this high dimensional space? And then from that start to bias this so that maybe the red parts might be the red is likely the high energy and the blue would then be the low energy. And gradually I should then push my simulations to only sample the blue parts. And what if this works, and I think we'll do that eventually. I think the idea for us is not necessarily to do this to refine a structure, right, but really sample the entire ensemble. If you have a channel, the channel is occasionally open and occasionally closed. And I would like my simulation, if it should be closed 10% of the time, 10% of the time in my simulation we should be in the closed state, but 90% we should be in the open state. And this way, I would actually be able to apply restraints from one open density and one closed density. And it would, the way I apply it with maximum likelihood, the fitting potential would encourage them to be either open or closed, but not right in the middle. And we'll see how far we get there. But this is going to be available in the beta of GROMACS that we'll release in about a month and a half from now, and it's going to be generally available before the end of the year. With that, there are a bunch of people here that I need to thank, in particular Shore's team. We have Takanori, who is instrumental for all the multi-body stuff, and then we have Yasenko here is going to talk about some of his own stuff. And we would be completely lost in the lab without Alexis' group, and particularly Shintaro has been amazing teaching both me and all the other people how to do cryo. And then to all of you, because it's an amazing community to get involved in as a beginner. Thank you very much.